My name is Neerja Arora and I'm working as an assistant professor in CSE department at Ajay Kumar Garg Engineering College, Ghaziabad. So today I'm going to discuss the topic advanced data structure binomial heaps, which comes under the subject design and analysis of algorithms having code KCS 503. So in this particular lecture, I'm going to cover these topics. First, binomial trees, its overview and its properties. Then binomial heap and various operations that we can perform on binomial heap, that is creation, insertion, searching, decreasing the value, extracting the value and deletion operation. So before going to start with binomial heap, first we know about the binomial tree. So basically a binomial tree is an ordered tree which is represented as Bi, where I is the order of the tree, and it is having the following four properties. First property is that if we are having a binomial tree of order I, that is Bi, and then it has 2 raised to power I number of nodes. And second property says that a binomial tree of order 0, that is B0, will have a single node or individual value. Third property is that the height of binomial tree Bi will be I. And fourth property says that a binomial tree of order I has a root node whose children are the root nodes of binomial tree of lower order, that is I minus 1, I minus 2 up to 2, 1 and 0. For example, as you can see in this tree, here we are having a binomial tree of order I. So the root node of binomial tree Bi will contains the child node or binomial trees of lower orders, that is Bi minus 1, Bi minus 2, I minus 3 up to B1 and B0. It means a binomial tree Bi is a collection of binomial trees of lower order, that is I minus 1, I minus 2 up to 0. So these are the few examples of binomial trees of several orders. In the first case, we are having a binomial tree of order 0. So the property of binomial tree says that if the order of the binomial tree is 0, then it will contain only a single node. Okay. And in the second case, the binomial tree of order 1, that is B1, is shown. So in this particular tree of order 1, we are having a root node, and that root node will contain a child node, a binomial tree of lower order, that is B0. Okay. So B0 will be the child node of this particular root node of the binomial tree B1. And this is the third case in which we are given a binomial tree of order 2, that is B2. So the root node of B2 will contain the two binomial trees of lower order, that is B1 and B0 as its child node. Similarly, in the last case, we are given a binomial tree of order 3, that is B3. So in this particular binomial tree B3, the root node of B3 will contain the binomial tree B2, B1 and B0 as its child node. So basically, a binomial tree of order I is a collection of binomial trees of lower order, that is I minus 1, I minus 2 up to B1 and B0. So this is a funda of binomial tree. So next comes to a binomial heap. So basically binomial heap H is a collection of binomial trees that satisfy the following two properties. So first property of binomial heap is that every binomial tree in binomial heap H should satisfy the min heap property. That is, the key value of a node is either greater than or equal to the key of its parent node. That is, the root node of a heap ordered tree should contain the smallest key value in the tree. And the second property says that there can be 1 or 0 binomial trees for each order, including 0 order. That is, we cannot have 2 binomial trees of the same order of same size in our binomial heap. And this property also implies that a binomial heap H having n nodes contains at most log n base 2 plus 1 number of binomial trees. So, if we are having a two binomial trees of same order in our binomial heap, then it is not allowed, and to resolve it we have to link them or merge them together in such a way that the root of one will be the leftmost child of the root of the another. That is, a binomial tree bi minus 1 having the minimum value at the root will be the root of bi, and the other bi minus 1 tree will become the leftmost child node. Suppose, let's understand it with an example. Suppose we are having a binomial tree of order b1 in our binomial heap, and also we are having a binomial tree of order b1 in our heap. Suppose in our binomial heap we are having two binomial trees of same order. So this case is not allowed. We cannot have two binomial trees of same order in our binomial heap H. So how we merge them? First we compare the root values of these two trees. So here the value 3 is less than value 5, that is the root value of right binomial tree b1 is less than the value of the 5. So after merging we get a higher order binomial tree, that is b2, in which the root node will be the 3. जो इनमें से मिनिमम वैल्यू होगी वही हमारे बायनोमियल ट्री b2 का रूट नोड होगा 3, and another binomial tree will become its leftmost child like this, and its child will remain as same. Okay, so this is the case, this is the method how we can resolve this issue. Basically the funda is that in our binomial heap we cannot have two binomial trees of the same order. So next is a linked representation of a binomial heap. So in a binomial heaps, each node n will have its value field that stores its value, and a degree field that stores the number of children the node n will have, and we are also having 3 pointers. One is parent pointer, then child pointer and sibling pointer. Parent pointer basically points to the parent of the node n, and child pointer of the n points to the leftmost child of that particular node n, and sibling pointer points to the sibling of n which is immediately to its right side. And in any case, if n is a root node, then parent pointer of that n will be null. Obviously if it is a root node, then it parent node nahi hai, so parent pointer parent of n will be null, and if node n has no children, then child pointer of n will also be null, and if n is the rightmost child of its parent, then sibling of n will be nil. Let's understand it with an example. Suppose we are given a binomial heap this, and this is a linked representation of that particular binomial heap. So let's consider a node value node 7. So node 7, this is a linked representation of the node 7, in which the val field will contain the value of node, that is 7, and the degree field will contains the number of child nodes of this particular node 7, that is 2, and this is a parent pointer, as 7 is the root node, so कोई parent नहीं है, so that's why the parent pointer will contain the value null, and this is the child pointer. Child pointer basically points to the leftmost child of the node 7. The leftmost child of the node 7 is 11. So this field will point to the node 11. And this is the sibling field, and sibling pointer will point to the node immediately to its right. So 7 के immediately right में आपका node है 9. So that field will point to the node 9. Okay. And if this if any node is a leaf node, like जैसे 21, So its degree will be 0 because it is not having any child node, and its child pointer will also be null, and sibling pointer will also be null, and its parent pointer will point to its parent, that is node 14. So this is how a binomial heap or tree can be represented in the form of linked list. Next is, suppose we are given a binomial heap which is having n number of nodes. Then by using that value of n, we can calculate or find out how many trees or of which order will be present in our heap. So basically, the binary form of binary digits of the number of nodes n tells us which degree trees will be present in our heap. So the longest tree has degree log n base 2, and there are at most log n plus 1 trees in our heap. For example, suppose in our binomial heap we are having 9 number of nodes. Then first we have to convert that decimal value 9 into its binary form. So the binary form of this 9 is 1001. So in our binomial heap of 9 number of nodes, we will be having 2 binomial trees of degree 0 and of degree 3. That is, of degree 0 and degree 3. It will not contain a binomial trees of order B1 and B2 because their binary digit is value is 0. So this is how this is a way through which we can find out how many which degree trees will be present in our binomial heap. Now next comes to operations of binomial heap. So the first operation that we can perform on binomial heap is creating a new empty binomial heap. So to create a empty binomial heap, we have to use the procedure create binomial heap, which allocates and returns the object h, where head of the h or binomial heap will be set to null, and this procedure will take a constant time, that is big of 1. So these are the steps that we have to execute to create an empty binomial heap. First we have to allocate a object h, then set the head pointer to null, and at the end we have to return that particular object h. Second operation that we can perform of binomial heap, inserting a new node into a existing binomial heap h. Suppose we are having a binomial heap h and we have to insert a new node x into our binomial heap h. So for this particular operation, first we have to create an empty binomial heap h dash, okay, and for a given node x, we have to initialize all the pointers and variables. For example, first we have to set the parent of the given node x to null, and we have to also set the child pointer of node x to null, and sibling of x also be null, and degree of x also be null. Suppose so here we have to first initialize all the pointers for the node x. Then we have to set the head of binomial heap h dash that we have created in the step 1 to x. Okay, so the node that we have to insert x, so first we have to create a binomial heap h dash for that particular node x, and that the head of this binomial heap h dash will point to the node x, and this is the binomial heap h, which is the given existing binomial heap. So, and this in the step 4 we have to unite or merge these two binomial heaps to get the final binomial heap, which includes the node x, and this union operation will take big of log n time. Let's understand it with an example. Suppose we are given 7 number of elements, 5, -1, 3, 5, 7 and 8. So to create a binomial heap, first we have to take the first value of 5, and we have to create a binomial tree which is of order 0. So in binomial tree B0 we are having single node or single value, that is 5. Now next we have to consider or include second value, that is -1. Again we have to create a binomial tree of order 0, B0, because it is a single value. So now in our heap we are having two binomial trees of same order, which is not allowed. So to resolve this, we have to merge or unite or link these two binomial trees of order 0. So this is the output. After union or after linking these two trees, we will get binomial trees of upper order, that is B1, and the root node of B1 will be the minimum value of these two B0s. So here -1 is minimum. So in B1, -1 will be the root node, and the another tree will be the leftmost child of this -1. Now again the next value that we have to insert is 3. Right now we are having a binomial tree of order B1, and for 3 we will create a binomial tree of order 0. So both are the different order trees, so they both can be allowed in our heap, so no need to unite them. Again next value is 5. So now in our binomial heap we are already having two trees of order B1, B0, and again that value that we have to insert is 5, which comes under the binomial tree of order 0. Again two binomial trees comes of the same order, so we have to unite 3 and 5, and after uniting we will get a new binomial tree of order B1, and this is a previous binomial tree of B1. Again there is a issue. Now we are having two binomial trees of same order. Again we have to unite these B1 and B1 tree to get the binomial tree of upper order, that is B2. So कैसे unite करेंगे? First we have to compare the root node of both these trees. So -1 is a min, so the -1 will become the root node of B2, and the another tree will become its leftmost child, and its actual child node will remain as same. Similarly, we have to insert 7, 8 and 9, and this is the final binomial heap in which we are having a binomial tree of order 2, order 1 and order 0. So this is a final. So next operation of the binomial heap is finding the node with minimum value. So for this we have to execute the procedure or use the procedure min binomial heap for a given binomial heap H. So in this operation, first we have to initialize three variables, that is x, which points to the head of the binomial heap, the variable y, which is initialized to null, and the variable min, which is initially set to infinite value. Then we have to repeat or execute step 3 and 4 until x will not equal to null. So in this step 3 and 4, first we have to compare the min value with value of x. If the value of x is less than min, then we have to set min is equal to value of x and increment or set y to the x. Otherwise, we have to set x to the sibling of x. Let's understand it with an example. Suppose we are given a binomial heap. Okay, so this is a given binomial heap where head of h will point to the 12, which is the first tree of this particular heap. So initially x, we have to initialize the variable x to the head of h, that is 12. So x is 12, and we have to initialize the variable y to the null and variable min to the infinity. So in the step 1, first we have to compare the min value with the value of x. So x is 12 and min is infinite. So minimum value in between these two is 12. So this is an example. Suppose we are given a binomial heap in which we are having three binomial trees of order B0, B2 and B3. So initially the head of the binomial h will point to the first value, that is 12, and we have to first initialize all the variables. So the variable x will be equal to 12, which is the head of the binomial heap, and the variable y will be set to null, and the variable min will be initialized to infinite value. So in the first step, to find the min value of in this particular binomial heap, first we have to compare the min value with the value of x. So value of x is 12 and the value of min is infinite. So in between both of these, the minimum is 12. So we have to update the value of min variable, that is 12. So now the updated value of min will be 12 and the x will be shifted to the its sibling node. So the sibling of the node x is 7. So now the new value of x is 7. Okay, and the value of y will also be updated. The value of y will become equal to the value of x, previous x. So now y will be set to the equal to the 12 and x will be set to the 7. Again we have to repeat this procedure. Now the min value is 12 and the value of x is 7. So among these, the value 7 is minimum. So we have to again update the value of min variable, that is 7, and x will be shifted to its sibling node, that is 9, and y will be shifted to the x. So now new y will be 7 and x will be 9 and min will be 7. Again we have to repeat this procedure. We have to compare this value of min, that is 7, and the value of x, that is 9. So the min is obviously 7, so we will not update the value of min this time. So min will remain same, that is 7, and the y will remain same as 7, and x will be shifted to its sibling node. As we can see, there is no sibling of x, so x will be set to the null and the value of y will be returned. So 7 is the minimum value in this particular given binomial heap. So this is how we can find out the min value in a given heap, and this procedure will take time big of log n. Okay, so the running time will be big of log n, and there are at most log n base 2 plus 1 routes to check. Next operation is decreasing the value of a node. Suppose we have to overwrite or replace the value of a node with a new value k, which is less than the current value of a node. So this operation is known as decreasing the value of a node. So if we have to replace the value x with the new value k, where k is less than x. So to perform this operation, we have to execute these steps. In the first step, first we have to compare the value of k with value of the x, current value of x. If value of x is already less than the value of k, then we have to print error. And otherwise, we have to first replace the value of x with k. And after overwriting or after replacing, we have to initialize two variables, ptr and par. Ptr will point to the x and par will point to the parent of the ptr. And we have to repeat step 5 and 6 until parent par variable becomes not equal to null. And in this particular loop or operation, we have to compare value of ptr with value of par. If value of ptr is less than its parent value, then we have to swap both these value, and we have to set ptr to parent variable, and par will become its parent of the ptr. Let's understand it with an example. Suppose this is a binomial heap and we have to replace 11 with value 6. So first we compare the value k, 6, with value of x. So value of x is greater than value of k, so we can overwrite it. So after overwriting, we will get 6 here. Okay, so here the value of x is was greater than value of k, so we overwrite the value 11 with 6. Now we have to initialize the variables. So this is ptr variable, and parent of ptr will be initialized with par variable. So we have to compare the value of ptr and par. So here the value of ptr is less than value of its parent node. So we have to swap them. So after swapping, we get 10 here and we will get 6 here. Now after swapping, now this will become the ptr and its parent will become par. Okay. Again, we have to compare ptr with its value of its parent. So here ptr is again less than its parent node. Again we have to swap them. So here comes the 8 and here comes the value 6. Okay. So after swapping, we will get 10 here, then 19, here we will get 8, here we will get 6 and here is 5. So now current ptr is this and this is, sorry, now current ptr will be this and par will be this. Again we have to compare the value of ptr and par. Now the value of parent is already less than the value of ptr, so no need to swap them, because at the root node we are already having the min value, and binomial heaps follows the min heap properties, that is the parent should be less than its child node. So here we will stop. So this is a procedure of decreasing the value of a node, and this procedure will take big O of log n time, as the maximum depth of a particular node x will be log n. Next operation is extracting the node with minimum key. So the min extract binomial heap procedure basically accepts a heap h as a parameter, and it will remove the node with minimum key from the binomial heap. So to delete or remove the minimum value from a binomial heap, we have to follow these steps. So in the step 1, first we have to find out the root node which is having the minimum value in the root list of the binomial heap h, like this. So suppose we are having we are given a binomial heap and in the root list of this particular binomial heap we are having 18, 8 and the value 4. So this is the root list of this particular binomial heap, and in this root list the minimum value is 4. So first we have to find out the minimum value in the root list of h. So after finding, we have to remove r from the root list of the h. So here we have to remove the value 4. And after removing the r from the root list of h, we have to create a new empty binomial heap which returns a pointer h dash, and also we have to reverse the order of r's children, thereby forming a linked list, and set the head of h dash to point to the head of the resulting list, and at the end we have to unite the actual binomial heap h and the new binomial heap h dash. Let's understand it with an example. So in the root list the minimum value is 4. So first we have to remove the 4 from this binomial heap. So after removing the 4, we will get the 4 separate binomial tree of order 0, order 1, order 2 and order 3, like this. And after getting the separate binomial trees, first we have to reverse their order. Okay. So at the leftmost side we have written the binomial B0, binomial tree B0, then B1, then B2 and B3. We have to reverse their order. Okay. And we have to initialize the binomial tree B0 with the head pointer of the new binomial heap H dash. And in the last step, we have to unite both these binomial trees, initial binomial tree, binomial heap H and the new binomial heap H dash. So after union operation, so this is the final binomial heap. And how we united them? First, at the leftmost side, we have to write a binomial tree of lower order. So in this case, the 36, that is B0, is a lower order tree. It will comes to the left, and then 14 and 21, this tree is having order 1, and in this heap we are also having a binomial tree of order 1. So same order trees are not allowed, so we have to first merge them or unite them to get B2. So this is the final binomial heap after merging these two binomial heaps. Thank you.